Hello everyone, my name is Alex Warden, and I'll be presenting on the paper Application Level Autonomic Hardware to Predict and Preempt Software Attacks on Industrial Control Systems. Before getting started, I'd like to give a few acknowledgments. The authors of this paper are Lee W. Lerner, Zane R. Franklin, William T. Bauman, and Cameron D. Patterson. They're all part of the Bradley Department of Electrical and Computer Engineering at Virginia Tech. This paper was presented at the 44th Annual IEEE International Conference on Dependable Systems and Networks. I provided a link to the paper if you'd like to take a look. Here's a quick overview of what I'll be covering during this presentation. First, I'll give an intro to embedded systems and threats for those of you who aren't familiar, and then touch on some threats that are inherent to industrial systems. Then I'll discuss the current approaches to process security. Many of them are antiquated and are having a difficult time keeping up with evolving threats. Under this section, I'll cover ICS independent security techniques that are implemented across a wide array of enterprises, and then touch on ICS specific techniques that most of us should be familiar with at this point. Then I'll discuss the trusted enhancement of critical embedded processes and some of its components. I'll also discuss the limitations and trade-offs to implementing TSEP. When securing any system, whether physical or cyber, there are inherent trade-offs and limitations. I'll be providing those specific to TSEP. Then I'll walk through a real-world example of how TSEP is implemented through a simulated deployment of a motor control process, and discuss some of the real-world value it adds. And then finally, I'll provide a conclusion on the relevance of implementing better security to embedded processes and how the authors of this paper are trying to tackle that issue. So, embedded systems' role within an ICS. Industrial systems are a mixture of conventional and embedded computer platforms used for automation. Examples of conventional systems are workstations and supervisory hardware used to control more specific computing platforms, which are leveraged by embedded systems. So what is an embedded system? An embedded system is a combination of hardware and software designed to perform a specific function within a larger system. Each system can be designed to be programmable or perform a fixed function. Embedded systems typically utilize basic processors because they do not perform complex functions. So in this situation, embedded system is much more likely to utilize an ARM instead of an x86 processor. Some examples of common embedded systems include RTUs, PLCs, and IEDs. Ultimately, embedded systems provide a bridge between the cyber and physical worlds. So how do they bridge that gap? Well, embedded systems enable supervisory systems to control the outputs of industrial systems. So what are some threats to security? Well, as automation increases, the threat of malicious reprogramming of processes of control systems becomes more apparent. So there's potential for large-scale disruption and destruction that can be caused by malicious reprogramming of control systems, or process control systems, rather. Prime example being Stuxnet, and more recent, the attacks on the Ukraine power grid, where attackers overwrote firmware on devices. Now, the latter isn't specifically targeted at control processes, but it shows that adversaries have that capability. If you'd like to read more about the campaign on the Ukraine power grid, give the book Sandworm a look. I read it. It's a very, very good read, and I think it provides a lot of useful information relevant to this course. So why are threats becoming more apparent? Because zero-day exploits are made more available to the public. It's been demonstrated that vulnerabilities specific to industrial systems cannot be mitigated in a timely manner. So accompanying this information is the underlying issue that it is difficult to attribute attacks to specific persons and organizations because anyone with internet access can develop and deploy cyber weapons. Another reason that threats to security are increasing is the combination of conventional and embedded systems increases the attack surface of an ICS, as ICSs have become a larger target for adversaries and malicious actors. Although most attacks focus on modifying commands to control systems, modifying firmware or control code can achieve the same effect. So, an example of how the attack surface is increased, well, conventional systems such as SCADA servers or enterprise networks provide avenues for adversaries to gain access to embedded systems and modify the control code or firmware. So what is the current approach to process security? Well, security and process control is centered around a design model that accounts for a correction of disturbances. The steps to do so is first creating a mathematical model of the system, either from physical laws, more specifically inputs and outputs of the system, or by acquiring and analyzing real data. Then using this physical system model, or this design model and data, using it to develop an effective control algorithm that can account for disturbances and modify the control process as needed. Simulating the response of the system to inputs such as a unit step change, where WT is the desired program process state, means that as the desired state changes, modifying as it changes and affects the environment, using a unit step change to account for that disturbance is what you'd want to simulate to ensure that it responds effectively. And then synthesizing controller code for a particular embedded platform. Embedded platforms are very specific and they aren't typically general use. So for different controllers or control processes, you typically have to develop code for that specific controller. So the logical orders of steps taken by controllers based around this model. Well, controllers will periodically read sensor data, YT, from a physical process, either input or output, compute the error, ET, between the sensor data, YT, and the desired programmed process state, WT. And then finally, adjust process inputs, UT, in order to minimize the error. So this is the current approach taking to process security. But as you may notice, it is somewhat limited and does not account for malicious activity or malicious reprogramming of code. So what are some ICS independent security techniques? Well, hardware and software architectures leverage hierarchical control that trickles down from personal computing systems to embedded platforms. Again, touching on how conventional systems are mixed with embedded systems, you may have a supervisory workstation, or maybe an MTU, or a SCADA server that will pass information to embedded platforms to control that capability. So the main security control used here is defining zones of trust, where increased trust is granted to the hardware and software being utilized in that zone. Typically, inner zones provide services to outer zones. As the number of services increase, the complexity of the service providing code makes it likely that bugs may exist or be used for an adversary's advantage. Zones are typically broken out into normal and secure zones, which provides moderate security if you have applications running in different zones. But that is not the case most times. A lot of systems have applications running in the same zones and rely on defenses such as firewalls or receiving regular updates to ensure that connections and data are not passed maliciously or against parameters. So what are some ICS specific security techniques? Well, security solutions proposed for general use embedded platforms are not optimized for applications used within ICS, which drives the need for development of specific security techniques. The model-based design discussed previously, used for protection of process control, is useful for redundancy, but again, it is not optimized to defend against an APT. Fault detection is the main benefit to this approach. And then most ICS security techniques are reactive in nature. Example being runtime monitoring software on an MTU or SCADA server is useful for anomaly and threat detection, but require corrective actions before normal operations can be resumed. So what this may look like is seeing that a control system or process control system is out of sync and shutting it down until the parameters or the code can be rewritten to ensure that it maintains a steady state. Okay, so now we're going to talk about trusted enhancement of critical embedded processes. So for all intents and purposes from here on out, if you see plant model referenced, I will refer to it as either a physical system or industrial system, just for broadness instead of focusing on a plant. But anyway, a method developed, so TCEP, or Trusted Enhancement of Critical Embedded Processes, is a method developed to ensure process stability by creating an environment where configurable hardware does not rely on trust from upper layers of an ICS architecture. So this is a new age model for active defense that cannot be disabled by any command and control systems, is transparent to the operator, and can anticipate future controller behavior. This also provides the flexibility to adapt application parameters in defense of specific industrial systems using field programmable gate arrays, or FPGAs. Here's an example of the TCEP model. So here you'll see that the white boxes are typical controls design, and then the gray boxes are where TCEP injects itself to provide better defense and protection against reprogramming of code. So you'll see that there is verification sketching, which ensures that the code meets the system design. And then you have the TCEP source integration, where you ensure that it ensures that the plant model, or I guess physical system model, responds as expected. And then you also have a second verification box where you ensure that the code written performs the intended actions. And then once you have the verification conditions proven, which I'll touch on more in a moment, it is implemented in the embedded device. So what are the TCEP components? You have the production controller, which you see on the left, which is an untrusted stack of software that executes processes. Then you have the hardware monitor and backup controller. This is a trusted component that accounts for best known state and backup execution. You have the prediction unit on the right, which is the test bed implemented as part of the TCEP model. And then finally, you have the junction box in the middle, which coordinates all data transfers and timing functions. And of course, on the outside, you have the physical plant or the industrial system that is providing input to these different components. So what does the production controller do? Well, it's implemented through software running on the physical hardware, where it interacts with the programmable fabric through the AXI bus. It also sends and receives data through an input-output module. So it's getting data from either the physical plant or the hardware monitor. And there isn't much additional functionality with this component because it is used within the production environment. And when you have too much going on in there, it really could affect the the industrial system or the physical plant. So you really just want the code running on there and making sure that it can take inputs and outputs and use them to execute the code. Next up, you have the hardware monitor and backup controller. So this provides real-time monitoring of outputs from the production controller, physical system, prediction unit, and status code. Some of the inputs include as already mentioned, they include the outputs from the production controller, the physical system, prediction unit, and status code. As you can see in the figure, there's a specification guard that tests the outputs of the industrial system model, the physical system, and the prediction unit to ensure that they're within bounds. If any of them are out of spec or the code indicates an error, such as a bug or unsafe operating state, the backup controller will then be implemented and override the production controller output, where the production controller is the process control code. What the hardware monitor and backup controller really does is it integrates a stability preserving backup under the TSEP design model and allows for smooth transitions from production to backup controllers and vice versa, only if necessary. One thing to note is that there is a probation period to ensure that the production controller, if switched to backup, is not reinstated too quickly to ensure that the system reaches a good state for a defined time. So the prediction unit. What the prediction unit is it's a copy of the production controller as well as a model of the plant and the input-output module. It receives data across the bus through the junction box, such as commands from the MTU from the production controller. But what's really important here is that the prediction unit executes the complete software stack running on the production controller to test different states against the model when new code's introduced. One thing you can do is provide a software solution or provides a preview of attacks to controllers. It also operates in 4 modes. You have the save, where it stores the current state of both the system and the controller. Then you have restore, where it overwrites the current state with the last saved state if the code is bad. You have normal, where the software stack runs in a closed loop to test the code. And then you have accelerate, where it performs the same function as normal, except it's over an extended period of time to account for variation or disturbance. So how are they used? How are all 4 of these used together? So a processor in the prediction unit receives the start signal from the junction box, and the normal mode is run. That state is then saved, and then accelerate mode is used, and then upon completion, the state of the controller and the system before acceleration is restored, and the accelerated system model's output is passed through the junction box back to the hardware monitor. And this will be covered more in the example problem. Finally, we have the junction box. This is essentially the bridge between all of the different components. It manages system control and the flow of data. So now we're going to roll into some of the limitations and trade-offs of TSEP. So the limitations are, to enable it effectively, it requires programming expertise and manual intervention, which can be a burden for operators that work within an industrial system It also requires a constant synchronization of the system model and physical system to effectively manage states and changes. It also has the inability to remotely update the system model, which increases maintenance costs. The authors of this paper are working on a remote updating protocol, but it hasn't been released yet. And trade-off, so from a trust sense, application extensions. So from a trust sense, application extensions are independent of ICS architecture and code, which increases the security posture. It's also a low-cost digital logic alternative to classical mechanical safety measures. So instead of having an operator at an HMI turn off a valve if the water flow in a tank is too high, the TSEP will allow it to occur automatically once a bad state is realized. Now we're going to discuss a motor controller example. So this example uses an emulated motor system where the control flow is event-driven. I'll touch on the hardware monitor code analysis that is conducted and some of the the design behavior for the system, and then how the system interacts when malicious code is injected, and how the security measures can benefit the system. So here's a quick look at the control flow. So the logical flow of the data, logical flow of the diagram is software is initialized. It follows a 1 millisecond delay where all components remain dormant. The emulated system then reads the input from its own input-output module. The input is then read by the production controller and written to its own input-output module. The value is passed to the junction box, which triggers the prediction unit. And then after the prediction unit completes processing all outputs from the prediction unit, the production controller, physical system. Sorry, let me step back a second. After the prediction unit finishes its testing, all the outputs from the prediction unit, the production controller, and the physical system are passed to the hardware monitor, which triggers the hardware monitor to begin processing the data. And if the status of the system or code shows a good state, then that code will be written to the physical system and the production controller. If not, a backup controller will be put into effect, and the same process will occur again until they have a good known state. I'm going to run through some of the code or example code that was provided by the authors. This is an example of what would be deployed to the hardware monitor, and it calls the controller prediction, so the prediction unit, the specification guard, and backup controller modules. So real quick, so we'll start at the top. So the first behavior to note is the verify all valid starting on line 6. This ensures that the hardware monitor does not trigger backup condition whenever the guard does not detect an out of spec condition. So as long as the physical system remains in operating parameters, this verify all will ensure that backup is not triggered. The second behavior, starting on line 11, is verify any invalid. So what this does, it proves the point that the hardware monitor will always choose the backup hardware implemented control response when any unit is out of operating specifications. For this behavior, we assume that Y physical on line 7, Y Excel on line 9, or Y model has a value below Y min or above Y max. So this shows that, if the value is below Y min or above Y max, that means that the system is out of operating parameters. So that's really the important part of that code. I don't want to dig too much into the rest. Don't think it meets the intent of this, but the remaining code, lines 20 to 48, is essentially the safeguard for implementing the backup and ensuring that remains in a good state until the production controller and subsequently the physical system returns to normal operations. So system behavior. So we have 3 figures. The first figure, you'll see that malware is attempting to drive the maximum value. So what it's trying to do is put the system in an unsafe operating state, starting at 350 milliseconds. And this is an example of a system without any safety measures. In the second figure, it demonstrates behavior both without the prediction unit and with the prediction unit. And this is with the hardware monitor in place as well. So the hardware monitor without the prediction unit, you'll see that the plant reaches unsafe operating condition. And then once it's realized by the hardware monitor, the backup controller is enabled and it reaches a state where it's in safe operating conditions. With the prediction unit, it proactively recognizes that code has been introduced where the system will operate in an unsafe state, thus triggering the backup preemptively, ensuring that the system remains in a good state. And then finally, the third figure shows the system output with prediction and automatic backup of the production controller. So in this, the prediction unit is forecasting the effects of the malware, and the hardware monitor is triggering the backup. And you'll see that about 250 milliseconds elapses where it remains in a safe state. And then after the malware has ended, or once the prediction unit determines that the code is safe and will resume normal operations, the production controller the copy of the production controller on the hardware monitor is enacted, and the plant reaches a normal operating state. So these 3 pictures show you what it is, what it could be, and then what it should be. That's how I view those. So finally, we'll roll into the conclusion. So the threats surrounding industrial systems are growing exponentially, which requires a migration from traditional security measures to more sophisticated and targeted protections, more specifically focusing on embedded systems and process controls. The existing approaches of adding hardware and software layers to help secure applications is too generic, and they do not adapt well to evolving threats. Ultimately, TSEP offers a new and innovative method that provides a rigorous verification of application-specific hardware that has the flexibility to meet increasing security demands. So I think they're very valid applications, and the authors of the paper put a lot of thought into how to best approach security in terms of process control within the ICS. If you have any questions, feel free, post on the Piazza link. I'm happy to answer them. Thanks for coming to my presentation. I'm signing off.